Hello, everyone. My name is Zana Oshraf, and I'm Assistant Director for User Services at MIT.nano. We are organizing this Tool Talk series to introduce our users and our potential users, our industrial partners, with the new and exciting technologies. It's a monthly event, usually. This is our first virtual gathering, I assume first of many. And without further ado, I would like to introduce Christian from the Attolight, who will share with us the story of cathodoluminescence spectroscopy for advanced semiconductor scientists. And the only thing I will ask you, we are a lot of participants on the call today, so if you can turn off your video, it will be greatly appreciated because we will increase the bandwidth of this meeting. Christian, please.
Sure, thank you. Thanks, Anna. Thanks for having me virtually over here. So thanks for attending to this seminar. I'm very happy to be here. I'm Christian Monachon. I am the product manager at Attolight. And I'd say I probably have one of the most extensive experience with our tool, our main product in the company. And I'm here to basically talk a little bit about what we use this tool for, what is cathodoluminescence spectroscopy, and how it can help you. So the title of the talk is Cathodoluminescence Spectroscopy for Advanced Semiconductor Science. You'll see that it spans quite a few types of materials and problems. So this is where we are. This is the Swiss Federal Institute of Technology site in Lausanne, Switzerland, where I did my bachelor's, and then I flew to the US for my master's, and then came back for my PhD, and flew again to the US for my postdoc. And then I'm back. So I kind of like this place, it seems like. And also, if you happen to come by, please do feel free to come visit us in these buildings. So who we are a startup company. Although kind of an old startup, that's basically what you get when you try to start up in hardware things. Software is a little faster growing, but in our case, we currently have an installed base of 10 tools in the analytical market. So by analytical, I mean either academia or companies that provide some services for cathodoluminescence spectroscopy. We have 3 tools in industrial surroundings. So those are tools that are fitted for industry that can accept full wafers up to 300 millimeter in diameter. And we also provide service measurements on 3 continents. And also feel free to stop me as I'm going, or if you're interested, or you can keep your questions, and I'll be happy to answer at the end of the talk. So the first thing that I need to tell you is what is cathodoluminescence. So when you shoot electrons at a material, they can do several things. So you have several things happening. The first and simplest thing that can happen is your electron can bounce back, and then it's called a backscattered electron, or it can trigger some ejection of low energy electrons. Those would be secondary electrons, or it can excite deep levels in atoms and emit X-rays. And finally, it can excite a band gap or some type of plasmon, and the radiative decay of this band gap or plasmon will give you cathodoluminescence. So it's basically shooting electrons at the material and collect outgoing photons that are in the range I usually say between 0.1 and 10 electron volts. It does compare to photoluminescence spectroscopy in the sense that it's kind of close. You're really analyzing outgoing photons. The few interesting differances with it are, first, it's the excitation is not diffraction limited for the length scales we're interested in. So you have nanometer scale resolution. The excitation energy of your primary electron beam is much larger than any band gap. So you can be pretty sure that you'll be able to excite any material. So this means, for instance, you have diamonds, no problem. You don't need an excimer laser or whatever. You can really just use your electron beam. The excitation energy can be tuned, and this is critical because this allows you to control the depth of the excitation that you trigger. And this can be sometimes absolutely critical, especially when you have layers that emit very little light on top of other layers and things like that. And finally, it's intrinsically correlative. So the cathodoluminescence signal that you collect, just like when you use energy dispersive X-ray spectroscopy, it basically, it's not, you're not collecting this signal as opposed to another signal, but you can really collect the two signals at the same time. So that's to give you just a little bit of an overview. So historically, cathodoluminescence, so the phenomenon was discovered way back in the 1800s, I think. But it's only, I'd say, in the 1970s that it took off in terms of being used, because people realized that it was extremely useful for petrography. So for basically geological analysis, and that was really interesting at the time because it was used in oil prospection. So obviously you immediately get some interest when you're talking about oil, although these days it's less obvious. Right now, I think it's gaining more and more interest, mainly because devices are getting smaller. So photoluminescence is sometimes not enough, and it's got a bunch of unique advantages that really make it quite compelling, I think, nowadays, as opposed to 20 years ago, because 20 years ago, perhaps many technology would not really need cathodoluminescence per se. So historically, it's been used in two modes. The first mode is panchromatic. So basically, you take all the light you can, shoot it at a detector, and as a function of where you're rastering your electron beam, you record a signal. And you can see, if I compare the two images, you can see that there's really a wealth of information that can be gathered already from this, right? So you can see that the luminescence recorded does not correspond to any surface morphology recorded by the SEM. And even you can also compare that to backscattered electrons, so and get some insights also about the comparison to chemical contrast. The other, I would say, smarter way that I would say has been really around for quite some time, but has been really practical to use in the past, I would say, 5 to 10 years, is the hyperspectral mode. So in this mode, just like you do on the images shown on the left-hand side, you can record an image, but in this image, each pixel that you record will contain a full emission spectrum of the cathodoluminescent light from your material. This is key to, for instance, detect particular defects or particular states in a semiconductor, and things like that. Where can it be used? I think that's a legitimate question. It's been originally discarded as a really niche technique. I think it still is. It's not quite as widely usable as energy dispersive X-ray spectroscopy, but yet it's gaining importance in quite a few topics. So I'm going to put some bubbles with the topics in them. Those are general topics. This is by no means exhaustive, but I've kind of scaled the size of the bubble with what we see, at least with our service measurements, for instance, as the important topics. So the smaller the bubble, the smaller the field at this point. So the first topic is direct semiconductor. So typically 3,5 materials, 2,6 materials. So I'm talking about gallium nitride, gallium arsenide, indium phosphide, zinc oxide, cadmium telluride. This is really bread and butter for this technique. You can really show a bunch of things very easily. So this is really where it's at. Now, these materials are more and more made into low-dimensional semiconductors. I'm not yet talking about 2D materials, but I'm talking nano/micro wires and things like that. This is quite a big topic too, like nano diamonds, this type of thing. Then you have, I'd say, of lower importance, but yet with quite a bit of potential, indirect semiconductor. So just like in photoluminescence spectroscopy, for instance, any material, any semiconductor material will emit light, provided you cool it down enough. And this is really the case with silicon, where we've had some success, for instance, measuring dopant concentration locally. This is the case with diamonds, where again you can measure dopant concentration, you can measure, you can see some defects, and also with silicon carbide, where here you can really see a bunch of things because this is a material that's a little more, let's say, tricky to both elaborate and dope and everything. And yet it's really important because you have an up and coming power electronics industry behind this material. Then we've got several customers, for instance, in our case, working on alkali halide perovskites. This is definitely up and coming as a topic, and there, I don't have too many examples that I can share, but definitely we have we're seeing sort of an increase in the interest in CL in that community. Then it's been quite a bit used in plasmonics. Just because you have a nanometer scale probe and you can really excite plasmons quite easily. Then transition metals dichalcogenides. We're seeing a couple examples about those, although there I would say the array of applications is a little more tricky to really explain and encompass. And finally, we have life science, where we've had a couple successes. Primarily, I think the highlight is we've been able to tell some proteins apart, but this is definitely not our forte, and definitely not the things we do the most. So I'm going to talk about examples of in all these topics. Feel free to ask if the other two topics are of interest to you. We have a couple of them that we can share, and I'll do my best. So optical processes in semiconductors, I'm pretty sure that most of you guys are familiar with these concepts, but yet I think it's interesting to just do a little bit of a brush up. So when you excite a semiconductor material, typically you excite electrons from the valence band to the conduction band, and you have an exciton that's been created, right? And this exciton can recombine either radiatively, meaning it emits a photons as it recombines, or non-radiatively. And in your semiconductor band gap, you have perhaps some intermediate states or things that either prevent recombination or spur the non-radiative recombination part, or spur several steps recombination processes. And this is really what cathodoluminescence spectroscopy allows you to see in a very local way. So meaning if you have a nanometer sized defect, you can see it with cathodoluminescence and you can really locate it. Okay. Now let me switch to, or this basically segues into our vision of what a cathodoluminescence spectroscopy-oriented tool should be, and what it takes for successful high-quality science. So the first and foremost, and this is nothing we can do anything about, is creativity, but I think this is really you guys' job. But on our side, what we do is we are making our tool repeatable and data-driven, meaning we designed our tool to essentially contain the collection optics of the optical part of the microscope. We embedded it inside the electron columns and it's collinear. The advantage of this is that you have no optical alignment needed whatsoever, and you have a constant optical collection efficiency over a 300 micron field of view. So you can see both small and large objects, and if you have a variation in emissivity between two spots, you can be positive that this comes from your material and not the system. We want it to be, or science should be multidimensional, so you see more and more all these things about correlative microscopy, about gaining more and more insights with the same tool, possibly at the same time. So spatial and spectral, I've already talked about. This is the hyperspectral map. We made our tool temporal, meaning we pulse the electron gun with a laser. And so you can have ultra-fast information about lifetimes of ultra-fast decays. And finally, electrical, because cathodoluminescence spectroscopy mostly pinpoints radiative recombination, electrical properties measured, for instance, by electron beam induced current allows you to probe directly non-radiative recombinations. And this is key to really be able to have sort of this balance between radiative and non-radiative, okay? And we want it flexible because while we have a sense of what science is about these days, we don't know what it's going to be about in 20 years. And so our tool is mounted on a breadboard, and you can really tinker all you want with it. And it's also open from a scripting point of view. So most of the equipment that we install, you can access it via Python scripting, except for the most sensitive one, because then you risk blowing things up. This is just to give you a sense of what it looks like. So on the right-hand side, you can see a schematic of the collection optics. that, as I was saying, is basically collinear with the electron optics and allows you to have no alignment of the optical column. And on the left-hand side, you have you can see that you have the machine, and you can see that it's mounted onto a breadboard, and basically it's really just like a Lego. It's really modular. This is what it looks like. If I want to make a schematic, you can see that you can have several types of sources. So let me switch to the laser pointer. Several types of sources. You can inject a laser to do some photoluminescence spectroscopy via the optics, which is interesting because we can reach, I'd say, interestingly sized spot sizes. You can put spectrometers, you can put several types of sample holders and stages, and you have a whole bunch of different detectors. So we really see our tool as sort of a spectroscopy platform, as opposed to something that's really cast in stone. So everything is field operatable and stuff like that. So now on to application examples. So we've got a bunch of them. I've tried to make the list not too long because I don't want you to sleep at the end of the talk, but rather being entertained and perhaps interested. So I've tried to make 4 sort of categories out of the examples that I'm going to give. The first one is new materials characterization. So right now it applies to, I would argue, transition metal dichalcogenides, or TMDs, or metal halide perovskites. Next, you'd have, or I would argue, you have fundamental science. So really, if you want to do some physics deep down in your material, and this is really something but you think there's a new type of phenomenon or stuff like that. And then, so those first two example or categories are, I would argue, quite fundamental. And then you have less fundamental categories, but nonetheless extremely important. And in this, I put process development in semiconductor and statistics in semiconductor. So process development is really when you want to try to create a first device, and then once you have this device, what you want to do, perhaps you want to make it large scale, or to really upscale your production and stuff like that. And at every of these stages, so from the most fundamental, discovering new materials, to understanding, to developing something out of your material, to really expand your production, we have examples on all of these steps. So those are just examples that I can share, especially in the last 2 cases, because we work a lot with industry. There's a bunch more examples, but that unfortunately I can't share. So 2D materials. I'm kind of starting with the material that gives us a little bit of problems, in the sense that those are fragile beasts, and they're quite they're really thin and hard to spot. But here, one of our customer was bored or annoyed by the fact that the device he was making were always dirty, or he had extra layers in his TMDs and stuff like that. So one of our customer basically used cathodoluminescence spectroscopy to characterize TMDs by their absorption from the cathodoluminescence emitted by the substrate, and this allowed them to really improve their process, and is less sensitive to sample cleanliness than AFM, for instance, or even regular SEM. Then another of our customer studied strain variations in tungsten diselenide, and there he could really see the exciton peak move as a function of the position on the membrane. So those were essentially suspended membranes of boron nitride, tungsten diselenide, boron nitride sandwiches. Then metal halide perovskites. So typically we installed a tool in Cambridge University last fall, and they are really working heavily on this. But there's no paper out yet, so I can't share any of that. What our customer tells us, at least, is that these materials are typically nano-grained. And so we can really help highlighting the effect of grain boundaries, their shapes and morphologies, and things like that. This is another example where it was useful, where one of our customers essentially highlighted or described the growth pathway for lead methylamine iodide. Then on to more fundamental science. So this is using time-resolved cathodoluminescence spectroscopy. So here, basically, you're shooting a laser at the tip emitting electrons in your microscope, and you use this to emit bursts of electrons with a time scale or a pulse duration in the ballpark of 1 to 10 picoseconds. And this allows you to do some interesting physics there, because in this particular case, the impact of a single edge threading dislocation in gallium nitride on the radiative lifetime of the exciton was directly measured. So it's not inferred, it's really measured because you have a very small spot size, so you can see these dislocations using cathodoluminescence spectroscopy, and using time resolved, you can have an accurate vision of what's going on. This is another example of what you can do with time-resolved stuff, but this is actually not cathodoluminescence. This is using optics to inject light, and using pulsed electron microscopy to see the effect of this light. This is a group in Caltech that actually was able to directly image the carrier generation and diffusion in amorphous silicon, and basically they were able to pinpoint an unexpected ultra-fast diffusion phenomenon in that material. Which is kind of counterintuitive, because you're really talking about amorphous materials, so full of defects and stuff. So this is not done with one of our tools, but this is an option that we have mounted already at the customer site. So really pump probe spectroscopy using an optical pump to excite the material, and an electron probe to try and see how this material reacts is definitely something that is of interest. Now on to kind of more large-scale things. Radiative recombination losses in cadmium telluride solar cells. So remember, I was talking about being able to have consistent results on a large scale. For this particular application, it's really interesting because they needed statistics on large surfaces in order to really, for instance, I think in that case it was to measure the impact of treatment to passivate grain boundaries, and really they were able, using cathodoluminescence spectroscopy, to extract recombination lifetimes and things like that quite easily, actually. Now, also for process development, strain measurement. So this is one of our customers who was interested in evidencing the impact of a plasma treatment on indium phosphide, and he used polarization dependent cathodoluminescence spectroscopy, and this allowed him to really pinpoint where a strain was being created inside the material during the process, and this really improved the process greatly. Just another example of process development. When you create small scale materials such as these nanowires, it's always hard to tell, you know, is my material properly doped if I want to make a device with it. In this case, this is a customer who is interested in making third generation solar cells based on gallium arsenide nanowires. And he was able, using cathodoluminescence spectroscopy, to really measure N-type doping in this particular paper. But he's since then also measured P-type doping, and it's just a matter of having the right reference, and then you can really tell as a function of position and in a single nanowire where your doping is standing. Now on to like more large-scale production. This is an example that is quite close to industry. Yeah, probably that not everybody in this room is familiar with V-shaped pits in gallium nitride, indium gallium nitride devices. But these V-pits, like they're called, are quite important for the mechanism of hole injection into the multi-quantum well of these devices. So we're talking about light emitting devices and also micro LEDs, so the next generation display technologies. And so these V-pits are super important for these technologies, and it's important to be able to both characterize their size and density as a function of position. You want this to be of a certain size, of a certain density, and as homogeneous as possible across a wafer. So this is just an example of what's done with our industrial tool, where basically you stick a wafer in and you can measure these features across your wafer. I think for a 4-inch wafer, like in this case, it's less than 10 minutes to get a full picture. Of course, it's sampled, but it really gives a good idea of what's going on over your whole wafer. With this, I'd like to thank you for your attention, and the floor is now open for questions.
Regarding the life science that you mentioned earlier, what sort of proteins can be characterized?
Yeah, so as I was saying, I'm by no means an expert in this. I can send you the reference of the paper. Basically, it was collagen. And so again, since I'm not a biologist, I'm not too comfortable with these notions, but I think the gist of it is that with cathodoluminescence, we can tell apart human collagen from other collagens, such as beef collagens and things like that, which apparently in some instances can be very interesting because it's used in surgery and whatnot.
We have another question: how to control depths of the inches?
So to control depth in the ideal case, because then you're talking about semiconductor structures and heterostructures and stuff like that. But in bulk semiconductor, you just the deeper you want to see, the harder you hit with your electrons. So typically, if you use a 1 kilo electron volt beam, you penetrate your material within the first, say, 10 nanometers. And if you use a 10 kilo electron volt beam, you penetrate your material within the first 300 nanometer, 400, 500, depending on the material. And if you use, for instance, 30 kilo electron volts, then you'll go down about 2 to 3 microns. So that's what I'm talking about.
Thank you. What is the longest wavelength that would be reasonable to probe measure in this setup?
In this particular setup, I'd say bread and butter for us is 1700 nanometers, so 1.7 microns. That being said, we have for a particular customer implemented up to, I think it was 2.2 microns. That being said, the detectors that are available for the up to 2.2 microns are quite noisy. So you really have to think hard before you put that type of detector. Not talking about FTIR, which we haven't implemented at this point.
We have a couple more. Is there an application of cathodoluminescence to indirect semiconductors such as silicon or germanium? Also applications in metal nanostructures.
Yes and yes. So silicon, yes, definitely. I'd say the flip side or the challenging part of silicon is that, especially bulk silicon, the excitons can travel extremely far before they recombine. So having a local information, unless it's structured, is hard. But this is something we've done in the past, and I'd say really the highlight and the application that we've actually sold to a customer was measuring boron doping and phosphorus doping.
Can you do both photoluminescence and cathodoluminescence in your tool?
Yes. Of course, so photoluminescence, it's again, you know, we want our tool to be open, and so you have you can have a flip mirror and basically directly inject light into the tool. We have implemented a first version of this at the customers. I think the best spot size we were able to reach was about 25 microns. And now we've refined this, although right now, at this point, it's still in the lab, you know, type of characterization. So we've taken our optics out of a microscope and we've basically envisioned a best case scenario. And I think the best performance that we get in terms of spot size is about 9 microns.
Last one. What is the impact of patterns like in semiconductor gratings? Do you measure anything that has a grating pitch of less than 100 nanometer?
So you mean in nanostructures?
I assume so. Yes.
So can you come again, please? Because I'm not sure I got it.
What is the impact of patterns like in semiconductor gratings? Did you measure anything that has a grating pitch of less than 100 nanometer?
So we're talking about the semiconductor that's pattern. And then you want to know the impact of this pattern of the emission of light?
He's asking about the scattering of the nanostructure.
So the scattering of light as it emits?
Yes.
Let me think. What I can tell is, for instance, we have measured silicon photonic structures. So indium phosphide grown in a nanometer. Well, it was, I think, down to 200 nanometer size grooves or 100 nanometer size grooves. And that was really a pattern. And there, I mean, we were not limited by anything that we were seeing. We could see some signal. Does that answer the question? I'm not quite sure.
Yifeng, does it answer the question? Yes, thank you. And very last one, we have a couple people asking how they can contact you. Can you share your email?
Yeah, absolutely.
Okay, then I'll just share.
Yeah, and if you're interested, if you have materials that you're not sure are adapted or could be, you know, if you think cathodoluminescence could help you, feel free to contact me, and you can basically ship us your sample. We can try them on and see what happens.
Thank you very much, Kristen.
Well, thank you.
Clap. We have a little reaction button, so if you enjoyed the talk, please clap. And we'll talk to you soon.
Yeah, thank you.
Thank you, everyone.